Hi everyone, welcome back to the faculty presentation series at Compass. Today we have Dr. Tamay Özgökmen, someone who's made some outstanding contributions to the field of ocean sciences. Dr. Özgökmen has been at the University of Miami since 1995 and has been a professor here since 2010, where he teaches fluid dynamics and turbulence. And if you're lucky, you'll get to hear some really great stories in between the lectures. His specialties are in turbulent flows and transport in the ocean using numerical and observational approaches. And thank you everyone for coming.
Thank you very much. Thanks, Rachel, for your kind introduction. Good morning, everybody. The day after Halloween, I'm happy to see so many people, especially students coming here. So I'm going to start with a long review of my background because Roland said you have to talk about your background, so I started. Okay, so I'm from Istanbul, Turkey, and I went to this high school, which was actually a building that was established to collect Ottoman debt by Germans. The education was in German, by German professors, so I put it for Roland. And this is me with a best friend of mine. A few years ago when I visited the school again, we had a lot of these safes to put the money in the school. And he's a very famous surgeon, so if you need a plastic surgery, when you visit Istanbul, it's not a high probability, I can hook you up with him. Then I went to so-called Bosphorus University, so this is the university in a very commanding location over the Bosphorus. Bosphorus, for those of you who don't know, separates Asian continent and European continent. And this is like the top neighborhood in Istanbul, very good location. The university was originally established by Americans. It was called Robert College. This is a picture from 1880. Same buildings, didn't change much. It's a very small school. Entry is through a very tough examination. And so this is a fort that the Ottomans built to conquer Istanbul, which was called Constantinople, 600 years ago. It's still there. So they cut off the supply lines and then we took it over. Never gave it back, but who knows. So I went there for mechanical engineering degree, obtained mechanical engineering degree in 1988. And then I flew to Miami, okay? So at that time I didn't know, but it turned out to be that I migrated to the United States. That was 36 years ago. I came and received my mechanical engineering degree from Coral Gables campus, engineering department. Then I went to Dartmouth College. Dartmouth College is a very cute place in the middle of nowhere. Nearest civilization is like 100 miles, Boston. And then I was very happy to come back to Miami again, back to civilization, a lot of life, nightlife. So this is me in 1995, smiling stupidly to be back to Miami, okay? And then I came here to develop an ocean model called HICOM. Now it's called HICOM. At that time it was called MICOM. Miami Isopicnic Ocean Coordinate Model. And my role was to write codes to develop parts of the model, but then I hated that. And then my supervisor at the time told me, okay, if you don't like it, you have 9 months to go, and then I cut you off. Unless you get funding, your own funding. So I wrote 2 proposals to ONR, 1 proposal to NSF, and they got funded. And actually I called my parents, I said, okay, I'm returning, let's make a travel in the United States. And I came back home after 3 weeks, and I saw these 2 mails, and they said, your proposals are funded. I said, okay, then I'm staying. So that was like 28 years ago. But even when I had my funding, full funding as a postdoc, okay, they gave me the whole book here. I was postdoc for 2 more years, assistant scientist, assistant research professor. Finally, somebody put me on research track. And as Rachel said, I've been full professor since 2010. So what did I do over these 30 years? This is my 30th year. I was a PI on 55 grants and contracts. A lot of contracts. I prefer grants because the stress is much less. You have a lot of freedom of thinking. $55 million total. Not everything came here, but still these are the grants that I led. 150, actually one got accepted yesterday, 151 papers I'm very proud to be co-inventor with these three French guys of a US patented biodegradable drifter, which is commercially available through Pacific Gyre, which is a large drifter company in the US. We are actually negotiating with MetOcean, which is a Canadian company, and we have our own company. So we sold like maybe 1,500 drifters through this to make it available to other researchers. We don't keep them, we say, okay, this is our niche. We make them available to other researchers to enable other people to do their science. These are my students. My first student graduated in 2010. He's already a full professor in Istanbul. Marcello is a senior scientist in Italy. Gustavo, I just talked to him last week. He got promoted at UCAR. John had a postdoc at Yale. Then he got a very lucrative job in London. It's a risk management company, top risk management company. And then I heard he's in Africa. I don't know what happened. So Peng Wang is an associate professor near Hong Kong. Matt, I just talked to him 2 days ago. We are still writing papers. He skipped postdoc because he had a thesis on machine learning and he was hired just like that. So if you do machine learning, you get hired just like that. John is a postdoc at Scripps. Junfei is my current student, and then Anne is actually one of my famous, she's not my student, but postdoc. She became a provost of a major university in France and ran for president, but lost. Okay? So none is homeless. So CARTHE project, I'm going to talk mostly about CARTHE project, but some other projects. So this was a competitively funded project. Each round, there are 3 rounds lasting 10 years, 8 out of 250 submissions. The project funding, the funding institution funding these things was established for 10 years by BP, okay, and then they kind of dismantled after distributing 500 million funding. We got 43 million out of this 500 as CARTHE, and we are one of the 4 teams that can fund it through the whole cycle, okay, because they shuffled around. So what did we do? Just statistics, okay? When the project gets big enough, you just have to write some numbers, okay? Then I'm going to show some results. 226 peer-reviewed papers. These are not inflated because the funding agency checked every paper, okay? If it was climate-related, and we had one climate-related paper initially, they rejected it. This doesn't count. So they checked every paper that grant is acknowledged, is related to the project. Grueling process. It's like review of the paper after it got accepted. 226 papers, 63 different journals, and I'm most proud of this number, 458 unique authors. So this is the number of people who actually contribute to this project scientifically. 3 patents, one is the drifter, and we uploaded 700 observational data sets to a new agency for data management that was established by Gomri, and they will keep these things there until 2030. After that, the funding runs out. I don't know what will happen. Thanks. So you can get all the data freely. You don't have to ask me. You can go to Gritzy, search for it, and it's very convenient. I mean, super well formatted in gazillion different formats. We put a lot of effort into that. So how did this whole journey start? Okay, Deepwater Horizon. It started actually on my birthday 14 years ago. I opened New York Times and I saw this picture, okay? And I said, oh my God, this is like a super GFT problem, because I teach GFT every year, as you know, I have many students here. And if you are a GFT person, this is like a PV forcing generated vortex, or at least that's what I thought. Okay, here are the top 10 reasons why this problem was of great interest to me. It was the largest accidental marine oil spill, okay? Super high visibility. This thing was on the news, and CNN, New York Times, 90 days straight, and BP ended up paying $60 billion for penalties. They didn't go bankrupt. So you can see the power of the oil companies. Long lasting, 90 days. Usually the spill is 1 day, if something spills and you deal with that. 90 days, they couldn't close it. Why they couldn't close it? Because it was 1,500 meter pipe, 1,500 meter deep, coming from a small pipe that's 0.5 meter in diameter. They couldn't reach back. In fact, somebody asked Obama, oh, the US Navy has all these submarines, can you send one to close? And they said, no, it's beyond our capability. So the oil companies have more technological advantage. Again, this was probably an active vortex. In other words, the PV forcing was generating this vortex, and that means the oil spill was generating its own flow. It couldn't be considered as a passive thing that's pushed around by ocean currents. And then it was an area away from the mesoscale and coastal flows. So this area, it's probably not the best picture, but the loop current kind of comes here and turns around because it's in a canyon. And the Mississippi River outflow doesn't reach that far. So it's in this really like intermediate zone between the coastal forcing and mesoscale forcing. And I thought it was very, very suitable for some mesoscales I'm going to talk about next. Why is it suitable for some mesoscales? Multi-phase flow, gas, oil, water. It's not just very difficult. Provided challenges throughout the entire project. From pipe flow engineering to GFT flow, lots of turbulence. It was very close to my career. Okay, I thought, okay, this is Tamay evolving. Okay, through the plume. It was in our backyard. It was not on the other side of somewhere very close to, very far away from us. So it didn't make sense for us to get involved. It was right there. Okay, and money was very good. It was in fact astronomical for standards of other agencies. We got 5 to 7 millions a year throughout the whole thing. So let's go to submesoscales. What's the connection to submesoscales? The CARTHE project was really a big submesoscale project. Okay, that's the way to view it. At least in my mind, it was not about oil. So biggest dilemma of geophysical turbulence is that GFT, geophysical fluid dynamics, and CFT, classical fluid dynamics, have opposite energy cascades. Okay? Because strongly rotating high aspect ratio flows, anybody who has taken my GFT class or better my turbulence class knows these 2D-like flows, the energy cascade is from small scales to large scales. In our coffee mug or whatever, this is kind of my coffee mug here, the energy cascade is from large scale to small scale. So all of a sudden we see this very strange dilemma. Okay, if you have, let's say, Gulf Stream rings, how do they access dissipation? How do they die? Do they live forever? And you cannot track these. I try to track these things. Okay, what happens is that they form. If they form in the winter, you see them. In the summer, heats up. There's a capping layer. You lose them. And then after a while, they may be there. They may not be there. I just read a paper. This Norwegian guy is observing the same eddy for 6 years, north. So. Do they die? How do they die? How do they access dissipation? So this essentially brings us to submesoscale as being the bridging scales, okay, between the GFT flows and CFT flows. And we don't really know how they are generated. How do we recognize them? How do we observe them, track them, and so on and so forth? There are a pile of questions you can come up with. I just kept it short. This is from a figure from McWilliams. He keeps writing this every year. He writes the same review paper. Okay, he was part of our CARTHE project. He's Academy of Science member. And essentially, what he's saying here, I don't want to go into too much detail, is submesoscales are in this intermediate range where you have your GFT flows, hundreds of kilometers, thousands of kilometers, and you have your flows that you see every day. You go to the beach or whatever, take a shower, play in a UM's pool or something like that. These guys are in between, okay, 10 kilometers to 0.1 kilometers, hours to days, and they bridge these totally different characters of fluid flow. So ONR was very, very interested in this problem, and they started funding submesoscale research starting in 2008, and I've been in their submesoscale program ever since 2008, many, like 4 or 5 DRIs. This is from a typical ONR experiment. This was done in 2010. I was involved in this project. What you see here is 3 ships, okay, going around at different grids, tracking dye that was released in order to capture, hopefully capture submesoscale processes. Of course, it failed to capture, but I'm going to talk about that. 3 ships, 1 plane, pile of drifters, 3 weeks working hard like crazy. Okay, they really worked hard. I just want to give you an idea of how much hard work went into missing submesoscales. Okay. So typical group discussions in our meetings would be like every year the same for 5 years. What are we looking for, guys? Okay, what are we looking for? We tried, we cannot find it. How do they look like? Does anybody know? Theoreticians, please run your models and show me something that I can latch on, okay? Where can we find them? Okay, we cannot sail around. This was a big complaint by observation. We had 3 ships. ONR is committing all the resources, and you are not telling us where we find them. So what are we going to do? Go around sailing in the ocean and all that stuff. They were pissed. When can we find them? They prefer the summer, but it turned out actually winter is the best time, okay? So this is 2010, the same year as Deepwater Horizon oil spill, and it turned out all this stuff that I've shown you, chasing a dye released from 2 barrels of tracer. 2 barrels of tracer. Okay, they were chasing, because they have all kinds of permitting issues. You have to get permitting for a year. You release a dye, and then you chase the dye. Okay? Meanwhile, same time, this experiment is in April, this was in April. Deepwater Horizon oil spill was 4.9 million barrels. Okay, it was like, oh my god, I was like, oh my god, do I track 2 barrels or 4.9 million barrels? I take 4.9 million barrels. And it was actually, it turns out that oil is super tracer. You can see the features very well. You don't need a plane, you don't need sensors, you don't need anything. You just see it. So I started looking at these pictures again and again and again. And it was like a life-changing experience for me. I said, wow, look at the ocean, what the ocean is doing. A lot of concentration and then nothing. A lot of concentration and nothing. If you want to, let's say, act in response to the spill, what you do is you spray toxic material. And the planes were going over it and spraying. And they were spraying 90% of the area was actually fine. So they killed a lot of creatures. Okay, it's very difficult to respond if you have a patchy situation like that, and much of that can be traced to submesoscales. So how did this project start? The project started when I was sitting in my office on a Friday night. I remember very well, 6 o'clock, and I was pissed about, like, Rasmus was supposed to respond to the call, and they said, we are not going to respond, individual PIs have to respond. I came back to my office, I'm like, okay, what am I going to do? How am I going to, I really want to respond to this call. And Shui-chan, who many of you don't know her, but some of you do, of course, came to my office. She's my neighbor. Lisa is in her office now. She came, Tamay, let's do it together, okay? And then I said, oh, really? I had never talked to her about science before. In a matter of 30 minutes, literally by 6:30, we had something, not this beautiful, of course, we did it for the proposal. We sketch on my board this sketch. What's the sketch? The sketch is we have a pipe, something is coming from the pipe, it hits the surface of the ocean, and then it's subject to atmosphere. In fact, there was a hurricane during the spill, and that's how Shui gets in. She said, you cannot do it by yourself, you need atmospheric people. I said, okay. And then you have waves, and then you have, of course, nobody cares about the oil spill until it hits the coast. Okay? In fact, we found an oil spill, some of the students know, leaking for 15 years. Nobody cared because it was going out into the ocean, not onto the land. So when it gets closer to the land, you have the shelf, you have the river outflows, a whole lot of processes. Okay? So I said to myself, okay, this is a great problem. Okay? Let's do this. Okay? So CARTHE was formed around this problem. And the biggest difficulty was how do we keep a coherent team, because usually what happens is you get some people, they know what the project is all about for 1 year, maybe 2 years. The remaining 8 years, nobody knows what's going on. Everybody does their own little thing. No coherence. And that's a recipe for disaster, because I want this project funded for 10 years, not for 3 years, and be ejected. And a friend of mine told me at the same time, so a lot of coincidences. He said, wow, the most successful project of the US was the moon landing. I said, why? I said, I know, that's why I'm here. I was inspired when I was like 5 years old, I was watching it in Turkey. Okay? And I said, what is the reason exactly this project was successful? He said, because Kennedy was able to tell in one sentence what the objective was. So you see, he said, to land a man on the moon and bring them back safely by the end of the decade. So all of a sudden people could realize, okay, the moon, Earth, Something is going to the moon, lands, flag, and then something has to come up, comes back, splash, celebrations, timeline. He even tells the timeline, 1962. I said, oh my God, this is like incredible, you know, this one sentence you can see. And then in fact, the next day after he told this, 30,000 people applied to be part of this project somehow in the US. So, of course, my statements are not as sharp, okay? But I said, okay, every meeting I would say, where will the oil go? How fast? How much? Okay, so these are I want to keep it like sharp enough so people can remember, so they don't deviate into something completely different from the project. That was a kind of key. It's a lonely job, okay? You have to keep a lot of secrets to yourself because you cannot talk too much to others. So the second question becomes, also the other thing we got criticized for is, they said, well, you need to find people from biology, chemistry, blah, blah, ecology, all that stuff. And I reject all of these things, okay? I said we need to keep it like physics, ocean physics and engineering only, because I thought to myself, we find a lot of good application here. And I want to entrain chemistry people, but it turns out that they're all working for oil companies. I could not find one chemist, petroleum chemist, who is from academia. They are all hired, 100% hired by the oil company. So that was a challenge. I wanted a chemist, I couldn't find chemists. Why is this stuff that I just described such a hard job? First of all, the ocean contains swirls within swirls. You don't see it often when you look at the beach or something like that. It's not always visible, but sometimes it's visible. Like this basin in Asia, and visualization here is accomplished by sediments on both sides. And now you can see it's a rare picture. It's like, you get like once every blue moon, it's clear pictures. Usually when you deal with satellite pictures, it's clouds, okay? You see a lot of creatures, okay? So if you have an oil spill here, where will the oil spill go? Will it go there? Will it go there? It's a labyrinth. It's a labyrinth. So even for a frozen shot like that, it's a labyrinth. But this is not frozen, it's time dependent. In other words, if you ask yourself, okay, how will I go from here to Coral Gables campus? You take the causeway, turn left, US 1 until you see it on the right. Simple. Because the road is not changing. Now, imagine US 1 is changing, moving around, okay, while you are driving. And that's the problem with the oil spill. There's time dependence. Okay, the time dependence problem is best illustrated here. Consider a chamber, clockwise, counterclockwise, simple. Not turbulent, chaotic stuff, simple movement. And if I ask you, if I have an oil spill here, will the oil spill go to the right? Or if I have an oil spill here, will the oil spill go to the left? No. Without time dependence, the answer is no. The green line is the separating line. But if you have a little bit of time dependence, the answer changes. Here I have a yellow oil spill on the left. I have a, let's say blue. I don't know what color it is. Blue oil spill on the right. And so yellow should stay on the left, right? With little bit of time dependence, what actually it turns out to be is blue one goes to the left and yellow goes to the right. Because there's some weird stuff going on in this, what's called hyperbolic points, that I teach in turbulence class. The students are bored with that. But time dependence is also important, even when flows are simple. RF 1984, there's a very nice paper. He said, for transport purposes, chaotic transport to happen, you don't need complex flows. Time dependence is enough. Three-dimensional flows. This is a simulation that I apparently ran in 2011, just to show that if you have multi-scale flows, here I have a baroclinic instability at the top, here I will have a baroclinic instability at deep ocean, you get multi-scale flows, okay? So three-dimensionality matter. You have what happens in deeper ocean affects transport. This actually I ran it for to estimate the number of drifters for the CARTHE experiments, the first experiment. So let's get back to the oil spill. The oil spill contained multi-scale processes. There are a lot of stuff going on. Okay, so this is where the oil spill was, this is where we are. We have the oil spill happening here, some kind of weird thing going on here, away from, again, fresh water. Some of it is entrained into loop current, so that's like the mesoscale picture. but then we have this kind of picture. These are real photos, not fake, okay? And other types of pictures. So there are many processes that's happening at the same time. And the question for if you want to predict oil spill is which processes matter, because they are all different animals, okay? They linear cells have nothing to do with submesoscale fronts, which has nothing to do with mesoscale features, loop current. I mean, they live in a different world. It's like rich versus poor or something, I don't know. Completely different. So we came up with this simple idea because we didn't want to have gazillions of complex diagrams. We said, let's use a complexity metric. Complexity metric is a very famous complexity metric called finite scale economic exponent. So what it says is in short time scale or short space scales, complexity is high. Like if you want to look at your daily schedule today or since yesterday, you had to rush back home to put these masks and all that stuff, change your clothing, and rush to the party, blah blah, go from right to left, all that stuff, drink something. I mean, I'm talking to the students, professors of course. And then rush, early morning, come, drive through US1, come to this talk, and then your probably afternoon is also full. So in a daily basis, 24-hour basis, you have a very hectic schedule. But then if you are like me, okay, you come almost 60, and you think, what did I do in my life? Okay. The question is like, okay, maybe one or two things, okay? Not very much. So all of a sudden you have a great simplification as the time goes on. It's the same story here. This is the complexity, okay? This is this space scale in this case, but same idea. Or if you look at stock market, every day people are screaming, getting heart attack, but the market goes up and down, day zero, okay? So short time scales, you have a lot of players, a lot of stuff happening. This is where a lot of the ocean processes are. Long time scales, this is why climate is maybe a bit simpler than daily prediction. Okay? So we said, let's try to do this idea to see which scales control transport. So this is essentially what you do is you release two particles, drifters, delta distance apart. And delta goes from microscales to submesoscales to mesoscales to basin scales. Okay? So each, as you increase delta, change delta, the process changes. So you have to do it for many delta. And you have to look at how fast the drifters separate as a function of each process at different scales. The separation thing will be different. And typically you expect a power law distribution. We expect this because part of the spectrum has been covered before. People have found Richardson ballistic scaling kind of thing. Not in the very large scales you expect diffusion. But diffusion is really long and large time scales, okay? But nobody really released drifters on top of one another, like 100 meters apart, 200 meters apart. They thought it was stupid because I don't want to measure the general circulation. But then for the oil spill, what you really care is pipe is half a meter diameter. Okay, you wanna see how it evolves from half a meter to 500 kilometers. So there is no data for that. That's what I'm saying. For some businesses. So we had two hypotheses. Okay, the first hypothesis was, okay, submesoscales, small peanuts, they don't matter. Everything is dictated by dictators of the ocean, which is the mesoscale. So within the mesoscale, submesoscales move within the mesoscales. They are controlled by it, so they don't have a say. So this is obviously liked by everybody because ocean models do not have to use fine resolution. Observational people can just rely on altimeter. Happy ending, right? And this one is democracy across the entire spectrum. Everybody has a say. Difference can be huge. Okay? So this one people didn't want to really deal with. Okay? But we still have these two limiting hypotheses. Now the challenge became, how do we sample across the entire spectrum simultaneously? Because we had to release drifters at all scales at the same time. Okay? So to do that, we had our first experiment called GLAD. Once we got, yeah, sure.
I think I'll come to the microphone.
Can you explain what lambda was?
Lambda is 1 over tau. Sorry, it's not the same letter. This is lambda, 1 over tau. So 1 over tau is the how long does it take for the drifters to double their separation distance? 2, 1 over. Yeah. It's not the same thing like this. So this is this one. Any other? Yes, Igor.
Yeah, but you also you are talking about the oil and oil flows.
Yes.
So in a three-dimensional flow, it won't just spread. It can also accumulate in places where it have convergence.
That's right. Excellent point. I'll get to that, but we didn't know it at that time very well yet. Okay? At that time, we were like if you look at the oil spill at the end of the day, it's kind of getting big. Okay? So you're right. In the small scales, you have also some kind of convergence and so on and so on. That's the hair question. Okay? I'll get back to it in the second part of my talk. We have a lot of examples of convergence. This metric doesn't cover the convergence part yet. Actually, we tried to cook up with Angelique a coolant metric to do the convergence. In other words, reverse of this. So the question was initially, how do we deploy these drifters? And we were running models, but at the end of the day, we came to a point where we didn't trust the models because the models are good for general, but like for precise deployment, we said, okay, this is not great. So we actually made a deal with the US Coast Guard. We said, if you deploy your drifters, it turns out US Coast Guard is deploying drifters all the time for search and rescue, regardless of they want drifters there, they want drifters there, same drifters. Somebody knew that in the team. They said, well, I know this guy in the US Coast Guard, the top level guy, and I can tell you maybe they can deploy their drifters where we want because they're going to deploy them anyway and just deploy it doesn't matter to them from the plane. So, and then in return, I said, we give all our data to you free, 300 drifters. They said, okay, it's a good deal. So they deployed their drifters one day according to what we wanted. Then we came from Miami, and this is the canyon. This is where the Deepwater Horizon is. We made this what we call a large-scale survey. This is our large-scale survey. It's a space-filling pattern. It's a spiral. Okay? And then we did our first fancy deployment, which was called, as I said before, Grand Lagrangian deployment, 317 drifters simultaneously. It was the largest synoptic deployment at that time. Then we exceeded. So what is this fancy deployment? We have to cover multiple scales at the same time. So we have an S pattern, which is another space-filling pattern, on 10 kilometer by 10 kilometer area. Within this S, we had 10 nodes. Each node had 3 triplets. Okay? The first triplets were 500 meters apart, and the second triplets were 100 meters apart. Okay? So in this way, we could cover 100 meter pair separations, 500 meters pair separations, 2 kilometer pair separations, 10 kilometer pair separations, and then we could stamp this S multiple times and cover larger separations, all at the same time. How was that pulled off? We had one vessel, 2 small vessels. I mean, one large vessel, which is Walton Smith at the time, and 2 small vessels. And each small vessels had 3 drifters, great students who are great at sea. So actually we released these 3 drifters, 3, 3, and 3 at the same time. We were producing drifters in real time because it didn't fit to the ship, 300 of them. Okay, and how did it work out? This is the kind of what we want to stamp in the ocean. These are drifters as we are releasing. This is Walton Smith trajectory. As you can see, they are of course moving as we are releasing them, but we want to get something like that, right? And at the end, it took about 4 hours. We didn't even know how long it's going to take or whether it's going to work. But at the end, we got this kind of a multi-scale thing, okay? The blue lines look like the black lines. So we have our pair separations reasonably distributed. And then this is the whole experiment. This is Air Coast Guard. We are coming from Miami. We did our large-scale survey. Somehow we had to go back to refuel several times. And we are releasing. And after a while, it started looking real good. Okay, we said, oh my God, we can see everything that's happening in the surface of the ocean. Isn't that nice? And everybody was getting excited at that time. And then we had to come back to Miami because we are running out of money, time, and all that stuff. And then it's hurricane season, right? And then, boom, this is a Hurricane Isaac. Milan had a great paper on that. Passed right over our well-developed drifter areas. And then we got a lot of people contacting us. Oh my God, hurricane people contacting me. Wow, what's going on? This is great, and all that stuff. Okay, I agree, but I don't know anything about it. But thankfully, Milan knew a lot about hurricanes, and he wrote a very nice paper. And I'm going to show another plot. So, at the same time, NRL, I would say they have the best ocean models. They are very interested because they're very close to the experimental side, part of our team. They started running their models and they were checking how their numerical drifters move with respect to our real drifters. Okay? So this was a big deal for them. And at the end, we ended up writing this paper, which was published in Proceedings of National Academy of Sciences. And we have two major results for essentially two different institutions. First of all, what's the ocean doing? Is it democratic or dictatorial? Ocean is very democratic. Everybody has a say and they dictate on what happens in their own scale. So submesoscales are kind of active in the ocean. You cannot ignore them. Now, the NRL model, which is this hollow squares, they don't have submesoscales because they didn't have the resolution. So NRL model says no, the mesoscales dictate. They are dead in my model ocean. And this dispersion deficit, when we first got this, I talked to Greg Jacobs, a good friend of mine. He's running the whole show there at NRL. I thought he was going to get really pissed off. But he said, okay, Tamay, that's good, so we can do some work. And he took it very well. And I would say the NRL models are significantly better now, based on this experimentation. And not only better, they are now developed a whole scheme to assimilate drifters. They can assimilate drifters, they are very good. I mean, they really went a notch up, the whole effort. Then we said, okay, let's compare to Aviso. Aviso is, as you know, altimeter data. And we saw another huge difference with respect to Aviso, because Aviso doesn't have the submesoscales. They barely have the mesoscales. Okay. And then we published this paper, and then I got an email from JPL. They said, okay, are you going to the AGA meeting? Yes. We would like to meet with you. I thought they were going to choke me or something over there. But they were like, okay, this result is looking very bad for us. Yes. And what can we do about it? We would like to join your future experiments. Oh, really? Okay. So they flew an airplane. They joined our future experiment, two big experiments. The next instrument they deployed failed even worse. It was even worse result. But then the third one was fantastic. I mean, I don't know what they did. They published a paper, and they even have a huge project since running. They even claim they can do oil spill. Okay, so I feel like we contributed to both JPL sensor development and NRL modeling during this experiment. Of course, our immediate response was, okay, drifters are great, we need more drifters. We developed actually our own drifters because we want to release more and more drifters, and we didn't want to pollute the ocean with plastic as we did our experiments. So we developed our biodegradable drifters. They're like 90% biodegradable. That's done mostly by Cedric. And this is an experiment where we released 1,000 of these drifters in the winter, 2 ships. And our drifters spill look like the Deepwater Horizon spill. So I'm very proud. They are all released from the near the Deepwater Horizon site, 12 million data points, and covering the whole Gulf of Mexico. So this led to a lot of papers. Okay. Now these are like a summary of the instrumentation we developed, which didn't exist at the time of when the project was funded. I mean, we put a kind of a PowerPoint. It was digitally like a dream, but actually all of them became reality. Biodegradable drifters. This is Cedric, very proud of his drifters. We probably built like 3,000 or something, deployed half us and half other people. We actually had this is a picture I took from an aircraft we rented for a month. And this aircraft was looking over the ocean with 1 meter resolution SST. And then we would get this image get the patch of the ocean, get a very small JPEG or something like that. And this is here us finding molten smith in the ocean and transmitting by radio. And then they would get, oh, where are we? Oh, okay, there's a front too, because otherwise you don't see what's going on. There's a front here, let's go over there, something else. And then this was, we had a huge balloon, 3 meters in diameter. This is taken at Rasmus many years ago, early in the morning. You see how many people it takes to control it. And then we said, why don't we have a huge balloon? At that time, drones were forbidden. Can you believe it? You couldn't do research with drones during this period. It was forbidden by the university. Then, of course, we shifted to drones. But at that time, we couldn't use drones. So we hang this humongous camera, Canon camera, with the most expensive lens and most expensive camera you can buy, which is not that expensive compared to the experiment. And then we hang it from a vessel that we rented as a secondary vessel, okay, flying at the FAA limit of 500 feet at that time. And then we have a bunch of drift cards. Drift cards measure, or drift cards go with a 1 centimeter depth at the surface of the ocean, which is where the oil is. Okay? Drifters are like half a meter. And believe it or not, between half a meter to 1 centimeter, there's a huge shear because of the atmosphere, which I'm going to show you. And this camera will take pictures every 15 seconds for 4 hours. Okay? And then we bring it back and change the battery back up. And then the question became, this camera is swinging in the wind, and then some of the stuff it sees is really drift cards, some of the stuff it sees is waves, so how do you clean the data up? And we got a fantastic postdoc. We spent like 2 years on all the data and wrote fantastic papers out of that, so we could see the surface flows, independently from the lower, deeper flows. This is an X-band radar, which was developed by friends of Roland, but it was never tested. Very nice radar, but it was always used from land. And then we said, oh, but can we take it to ocean, to the ship, and so that the ship sees the velocities around? So this is how we tried it, and it worked very well. So this became a very popular data set because you can see what's around the ship. So the whole idea we had, the dream we had was, usually when people say, oh, there's a lot of data, what they mean is somebody took some data in 1990, in July, somebody took data in 2000, in whatever, December, in another area. So there's this whole scattered array of chaotic data sets, and you are supposed to do something with it. And we said, no, we need data on top of one another at the same time, over the same patch of the ocean. So this was our philosophy that we accomplished through using an array of sensors and observation systems. Satellite data is available to everybody. Okay. Then we go in there in this area and we have our drifters. Then we go in this area, we have our aircraft SST. Then we go into this area, we have our ship radar velocities. And then we go into the smaller area, we can see drift cards. Okay. This way we zoom 120x over the same patch of the ocean. Okay, simultaneously. Everybody's running their stuff on the same patch. You discover all kinds of weird things when you have a lot of drifters. This is when we said, okay, we have 200 drifters left, let's launch them all in the ocean. And what happened was, the drifters were released, 200 drifters over the size of Miami by a single ship, and they collapsed after a few days on the size of this room. So there's a huge sinkhole with huge velocities, vertical velocities. That's the characteristic of submesoscales. So this was published by in PNAS, very popular paper, my highest cited paper by now, just in 5 years. This is another area where we released, let me go back, look at how regular it is. Seven vessels simultaneously releasing this drifter array. It's a square, and within hours, okay, we get a line, frontal collapse. We call this the zipper, and it was, we have a very nice paper with Irina Ripina, who actually graduated with Mike Brown maybe, yeah? 20 years ago. Now she's almost a senior scientist at so. Again, front, high velocities, another submesoscale feature, and high W. This is another interesting observation. So this is a coastal experiment where we were leasing drifters, and I couldn't make any sense whatsoever of what's happening with the drifter. Drifters are moving in ways I've never seen before. I'm like just complaining the whole time. And then Hans comes to the rescue. Hans said, well, I can tell my SAR people to go over your region. We said, okay, great. Can you send us an image? He sends us an image the next day. And then I looked at this image, and Ed is not here. He said, let's put these things on top of one another in Ed's room. I'm like pushing him, superimpose. And he superimposes our drifters with Hans' image. All the drifters are on fronts. Then I said to myself, okay, how can we see these fronts? Can we see these fronts? So we were renting a house here. We jump on the small boat, and I'm looking for these fronts in the ocean. Can we recognize? And all of a sudden I pass this thing, whoop. Okay, you can easily see it was a great sunny day, no wind, nothing like that. And all the crap was on it, like oil. Our drifters were on it. All the, you can see these drifters were released many days before, without the front. I don't know. And then wave activity across is different. Okay, so the people wrote papers on the wave activity, why the wave activity is different. This is Milan's paper. We wrote a very nice paper with Milan. So what we did is we actually collected all our measurements, okay, and checked whether Richardson law. So Richardson was a very famous British fluid dynamics guy, and in 1926, when he was in London, he was looking at the factory plumes. It's an industrial revolution, right? And he looked at 6 factory plumes, and he wanted to quantify how they disperse. And he came up with this law. Actually, it's based on 6 factory plumes. 4/3 law. It's empirical. Here we show that across 5 orders of magnitude scale range, from a few hundred meters to hundreds of kilometers, the same law applies. Amazing. Okay, it holds in the ocean surface. And what Milan did was, he showed actually the only 2 places where this law breaks. One is under a hurricane. When the hurricane passes, Richardson law gets messed up. Actually, you see higher dispersion. But then the second star is when the hurricane is over, it collapses back to Richardson law after a few days. I forgot how much. Maybe a week or something like that. And then near the surface of the ocean, where you have like top 1 centimeter, you have a slight difference. This is where we made an attempt to measure all the way to 1 centimeter of the ocean surface. Typically, when you talk to an oceanographer, surface oceans is maybe 100 meters, 10 meters, 100 meters typically. Drifters, like they release across AML, 15 meters. That's considered the surface of the ocean. But actually, for oil purposes, the surface of the ocean is 1 inch. Okay? We said, okay, is there a difference between 10 meters and 1 inch? Yes, huge difference. So this is an experiment that was actually designed by a student, Nathan. He actually was a first-year student when he started with our GLAD, and then while he was graduating, he started designing his own experimental ideas. He developed, and he's now a professor at New Hampshire. So he said, okay, we can have drones, we can have these surface cards. He had some kind of polarimetric camera that he did his PhD on that looks at the waves without drifters and so on and so forth. Combine all the instruments, and we could plot a profile of ocean currents all the way to 1 centimeter, from 10 meters. And we saw the difference is like 4 times. Okay, so and most of the plastic and oil is in the upper few centimeters. And this was actually an AGU paper highlight. AGU contacted him later on and said, oh, we like this paper. I don't know what the highlight is, but I saw email. It's forwarded to everybody, okay? And of course, one of the problems, oh my God, is this correct? I'm a little bit slow. 10-year project. 10-year project means you can have an oil spill during the project. Okay, you market yourself saying, oh, I'm very good in oil spills and all that stuff. And then what if there's an oil spill? Oh, no, I don't want to deal with it. Okay. So In fact, there was an oil spill during our project, and I got contacted by the funding agency saying that, okay, you've been bragging about this every time. What can you do about it? Okay. So we actually, on the fly, like I'm talking about like one day, okay? We designed the grid, students went there, released drifters around the oil spill, and we provided these maps and data to the response agencies every day. So this is the spontaneous coverage of the drifters. This is the entirety of the drifters area that they touched. This is the center of mass. And the most interesting part about this was that the models failed dramatically because this area was in between two satellite tracks, and there was an eddy you see now stretching the whole spill area to the south, which was completely missed by models because they didn't have the data. See, this is stretching. Okay, so this was a success in that way. Let me accelerate a bit. Doing experiments in the open ocean is interesting, but apart from those who participate, nobody cares. That's my finding. So we said, let's organize coastal experiments in Miami with students, young students, middle school students, high school students, so they actually understand something about the ocean. So we actually have hundreds, maybe thousands of students come here over 3 years and deploy drifters in Miami Beach, Erasmus, blah, blah, blah. And they will highlight Miami Herald, and so on and so on. So they love it. Another question is, your drifters are not oil. So we had to go to a tank called Onset in New Jersey. That's 200 meters long, much longer than Brian's tank. And more importantly, you can put oil in it, okay? This is made for oil spill research. And then we spent a week there comparing our drifters to oil. It's a good agreement. As I said, my student Jean went to Yale, and her professor there was a big Arctic scientist. So he had this idea: we can take your drifters and then put in the new Arctic Ocean that's like less and less covered by ice. So he went to Arctic with Canadian Coast Guard and wrote a very nice paper on that. Let me skip this because I'm running out of time. We actually did more experiments in Onset where we released oil from a huge nozzle, 1 inch. Because in laboratory experiments you have only like a needle, 0.1 millimeter nozzle, because the whole thing fills up with oil. And the big deal in this is that you need to have the particle size distribution, droplet size distribution. That's a big thing with the plume models. So Cedric designed this instrument that can actually see all the particles, and then we had a software that plots this particle size distribution from this graphs, and then that feeds into plume models. Yeah, a lot of fun. Nobody invited me. And we won 2 movie awards. There were like 5 movies made, short film, like 4 minutes, okay? By the votes of 100,000 K-12 students in the United States, so it's not. So, life after CARTHE, okay? Life after CARTHE is much less work, but I still had some projects at about $1 million each. ONR Calypso, it's completed now, and this was based on the idea that for submesoscales, W is important, and they want to measure W in the ocean. So we had a lot of drifters deployed. We had 3 major cruises. We went to the Mediterranean Sea, where there are these permanent gyres, almost permanent gyres. Great project. DARPA Ocean of Things. And this was very much inspired by CARTHE project. This DARPA guy saw our drifters. He wanted to release 50,000 for Pentagon to spy. Okay, so they trained me into this project, and the big difference between their drifters and ours is they had actually many sensors on their drifters. So they designed a slightly different drifter, but the big deal about this was sensors, multiple sensors. We had just GPS. And a very good group from Stanford designed this, but we didn't release 50,000, we released 4,000. California, Gulf of Mexico, Gulf Stream, these are Gulf Stream drifters, 1,500 or so. But then I find out from a friend in NATO, he works at the NATO center in Italy, that they released a lot of drifters of this in Ukraine war, in Black Sea and Hormuz Strait. No publications because project became increasingly more secret and we worked as a subcontract. No papers. Machine learning, we still have a very nice machine learning project that's going on, but for the interest of time, let me go to a summary. So, submesoscale features encountered. How do they look like? Okay, I'll give you 3 clear examples of submesoscale features. Density fronts, either from coastal forcing or surface forcing. So this is a very nice photo. When we are crossing this Mississippi River front, I took it from Walton Smith in one of the experiments, Mississippi, Gulf of Mexico. The front is half a meter in size, okay? Same here, half a meter. Or you can find a lot of NASA images where you have all kinds of fronts and convergence zones. Okay, so this is one type of submesoscale features, evolving very, very fast. Second submesoscale feature is spiral eddies. Cyclonic, always cyclonic, but because it turns out the anticyclones are unstable. We wrote a very nice paper with former student on the instabilities of anticyclonic submesoscale vortices. And actually Mark has a very nice paper based on visible images from Space Shuttle 25 years ago. And then very, very nice images. I put the one from Istanbul because this is near Istanbul. Cyclonic, 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 cyclonic. And this is in our experiment. This is from Alzheimer's moons and so on and so forth. So these are spiral eddies. They go inside. It's not like, it's not full motion. Okay, they go in, sucking in because there's huge doubling. Now, in our last experiment in Calypso, we actually went one step beyond and observed that one of these cyclonic eddies broke into 2. So that is like evidence for forward cascade that we were looking for. Now, this was possible entirely because we used our drifters to track, because this guy is moving so erratically, okay? If you have a ship, you will lose it like in 2 hours. But we put our drifters on it and receded. I was on top of it. And we could track the whole evolution because once you have the drifters, then the ship can go and put all kinds of other instruments. We actually have the 3-dimensional conical distribution of it. So this is I don't know what happened. They submitted these papers a long time ago, but I didn't hear anything. It's a very nice study. Finally, star eddies. What are star eddies? Star eddies are baroclinic instabilities, mixed layer baroclinic instabilities on top of deeper baroclinic instabilities. Mixed layers are very shallow, like 50 meters, 100 meters. So the baroclinic radius of deformation is smaller. So you have a huge discrepancy in the 2 places. So this is from actually an observation during a LATMIX program. We wrote a very nice paper with Angelique. This is from a model, so it's like more like a flower. And this has implications on what do you mean by LCS and so on and so forth. So to conclude, and I think I'm right on time, right? I can say that satellite and aircraft remote sensing are really convenient to kind of get you on the right place. But you need to have massive swarms of drifters, which I call Oceans PIV, to track these features. Okay, because they evolve on scales of hours and days and so on and so forth. Satellite data you may have, even aircraft, you may not fly all the time because of weather. Okay, and this we envisioned here. Actually, the first 10 years I was here, I was doing a lot of numerical things, and thanks to this project, we were able to do it in the ocean. And thank you for your attention.
Thank you so much. Do we have any questions in the audience or over Zoom?
Great. Nothing in the room?
Yeah, no, there's a person.
Question about.
I don't see anything in Zoom.
Yeah, thank you for giving an overview about the drifters. I'm interested to know that through all of what you mentioned, importance of the drifters, how expensive it is to deploy.
How expensive? So the drifter is actually maybe a couple $100, but then you have to. Most important part is data. So what we are doing is that you can buy the drifters from us for that price, okay? But then if you depending on what kind of GPS you use, okay, some, like this company that we have, that's a general drifter company, they not only provide the GPS, but also they provide the software to track it. So it goes to maybe 1,500 or something like that. But if you do it yourself, like if you just get the body, which is the most critical part, the GPS is maybe $100, and if you get it from data management from the GPS company, it's another $100 for 6 months. So you can really $600 fine, but if you go to the company, it's like 1,500.
Another question I have about, you mentioned about good for the oil tracking. What about if somebody is interested in plastic, like microplastic? Can we also use detectors to measure the microplastic?
Yeah, microplastic is we just had a paper published with a very famous microplastics guy in Europe. I don't quite understand, because the problem is that microplastics can actually go, so you cannot do the whole microplastic problem, because microplastics can sink. If the microplastics are very small, then the ocean currents can drag them down. And we know that for sure because Mariana Trench is full with plastic. Okay, so it's the deepest plane. So you cannot do the whole problem with drifters. Okay, you can do maybe part of it. Maybe you can say this is where they sink. Okay, but not track the whole thing. So it's helpful, but not the full problem.
I'm just thinking if you get the first order understanding. I'm not thinking of going in detail. Like
yeah, the first order, I don't know. So I was in this cruise with this guy for a month, and we talked a lot. And 90% of the plastics fate is not known. So people don't know. They cannot have a budget. Okay, so they don't know 90% of the problem. And he was very interested in working with us, with Cedric, on this thing. So it's a very good problem. Okay, I like this idea of this, but I'm not sure how much of that we can do. And they don't know either. Okay, nobody knows because it's small, and it's very difficult to even quantify. So what they do is they actually measure the whole column, collect water samples from the whole column, and they know at which depth how much microplastic is there, and they are kind of mapping the oceans with that. That's the current state as far as I understand. And most of it comes from the rivers. You asked, this lady gave a talk a couple of weeks ago. Most of it is in near Asia. Why it is in Asia? Because they collect all the plastics from the rest of the world. US ships all the plastics to Asia. It's not produced there, everything. So it's a very interesting problem and good problem, but tough. Yes. Right.
Okay, GFD quiz.
Yeah.
Anyway, beautiful talk, incredible.
Thank you.
You mentioned that a half-meter pipe of grease is a significant enough buoyancy source in the ocean to drive its own GFD.
That's what I thought.
Yeah.
That's what I thought. And I skipped that part for time of interest. Thanks for asking this question. So we actually had this idea that this can create a lot of forcing. Then we ended up doing the problem of what happens if you're a plume in a rotating environment. Why? Because this plume lasted 90 days. It's not just the oil parcel takes maybe 1 hour to traverse, but it's there for 90 days. So numerical conclusion was it generates its own precession. It's like a top, top, you spin it, angular momentum, it starts to go. And then we said, oh my God, can this be true? And then the Cambridge University people, who were actually part of our team for one of the periods, did the same thing in the lab, and they concluded, yes, the plume precession, in other words, the plume is going up, but at the same time rotating.
Yeah.
Like that. E is like 0.4 times the Coriolis. We never got to the active plume kind of thing, vortex forcing, which was nobody did that. So I had a lot of ideas initially, and then some people caught on to some of my ideas, some people totally ignored, and I didn't have time to do it myself. Like this vortex problem, which I thought this was a kind of a PV forcing driving this vortex, nobody did it. This didn't last very long because they came and started cleaning it.
Yeah. And that's
So
a cyclone, not an anticyclone.
Exactly. So it turned out to be funky.
Okay.
But
yeah.
it inspired me nevertheless.
Yeah, beautiful.
Do we have any other questions?
Thank you.
All right, thank you.